Imagine a place where the foundational rules of the universe, the very laws of physics we thought were unbreakable, begin to crack under pressure. A world of quantum anomalies, where symmetries we hold to be sacred are unexpectedly broken, and the neat, predictable order of the classical world gives way to a reality that is far stranger, more subtle, and more profound. This is not a distant, hypothetical realm. It is the very fabric of our own existence, a fabric that, when examined at its smallest scales, reveals a universe that is not just stranger than we imagine, but perhaps stranger than we can imagine. Today, we journey into this enigmatic world. We explore these mysterious breakdowns in symmetry, these glitches in the cosmic code that reveal the deep and beautiful gaps in our own knowledge and challenge our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos itself. At the heart of quantum mechanics lies a world that is fundamentally different from our everyday experience. It is a world of probability, of potential, of a reality that is not fixed until it is observed. This world is governed by a set of deep and elegant symmetries, principles that suggest that certain properties of a physical system should remain the same even as that system undergoes transformations in space, in time, or in its own internal configuration. These symmetries are not just beautiful mathematical abstractions. They are the source of the great conservation laws that form the bedrock of physics, the conservation of energy, of momentum, of electric charge. They are the source of the universe's order and predictability. But in the quantum realm, these symmetries are not always absolute. An anomaly is a situation where a symmetry that holds true in the classical world is unexpectedly and mysteriously broken by the subtle and powerful effects of quantum mechanics. These anomalies are not mistakes in our theories. They are profound and revealing features of nature itself. They are the places where our classical intuition fails, where the universe whispers to us that there is a deeper, more fundamental layer of reality that we have yet to fully comprehend. They are the cracks in the edifice of our current understanding, and it is through these cracks that the light of a new, more complete physics may one day shine. The standard model of particle physics, our current best theory of the fundamental particles and forces, is a triumph of 20th century science. But it is an incomplete triumph. It does not include gravity. It does not explain the existence of dark matter or dark energy. It does not tell us why the particles have the specific masses and charges that they do. Quantum anomalies are the signposts that point us towards the physics that lies beyond the standard model. They are the clues that will guide us in our quest for a more unified and comprehensive theory of everything. In this journey, we will explore some of the most fascinating and important of these quantum anomalies. We will begin with the quantum anomalous Hall effect, a strange and beautiful phenomenon where the quantum properties of a material can mimic the effects of a powerful magnetic field. Even in its complete absence, we will then delve into the world of chiral anomalies, which deal with the handedness of fundamental particles and reveal a deep and mysterious asymmetry in the laws of nature, an asymmetry that may be responsible for our very existence. We will explore the conformal anomaly, a breakdown in the symmetry of scale that has profound implications for our understanding of quantum gravity and the nature of space-time itself. And we will confront the gauge anomaly and the gravitational anomaly, deep mathematical puzzles that lie at the very heart of our attempts to build a consistent and unified theory of all the fundamental forces. Each of these anomalies is a window into a deeper reality, a glimpse of a universe that is more subtle, more interconnected, and more mysterious than we ever thought possible. They are not just problems to be solved. They are invitations to a new way of seeing, a new way of understanding, a new way of being in relationship with the strange and beautiful quantum cosmos we call home. The story of the quantum anomalous Hall effect is a beautiful illustration of how a deep theoretical concept in quantum mechanics can manifest as a real, measurable, and technologically relevant phenomenon. It is a story that begins not in the quantum realm, but in the classical world of 19th century physics. In 1879, the physicist Edwin Hall discovered that when an electric current flows through a conductor, and a magnetic field is applied perpendicular to the current, a small voltage appears across the conductor, in a direction perpendicular to both the current and the magnetic field. This Hall voltage is a direct consequence of the Lorentz force, the force that a magnetic field exerts on a moving charged particle. The magnetic field pushes the electrons in the current to one side of the conductor, creating a buildup of charge and a measurable voltage. The classical Hall effect is a simple, elegant, and incredibly useful phenomenon. It allows us to determine the sign and the density of the charge carriers in a material, and it is the principle behind many modern sensors and devices. A century later, in 1980, the physicist Klaus von Klitzing, working with a two-dimensional electron gas at extremely low temperatures and in the presence of a very strong magnetic field, discovered a quantum mechanical version of this effect. He found that the Hall conductance, the ratio of the current to the Hall voltage, was not a continuous quantity, but was quantized. It could only take on specific, discrete values, values that were precise integer multiples of a fundamental combination of physical constants, the square of the electron's charge divided by Planck's constant. This quantum Hall effect was a stunning discovery. It was the first time that a macroscopic, measurable quantity had been shown to be quantized with such incredible precision. It was a direct, macroscopic manifestation of the microscopic quantum nature of the electron's motion in a magnetic field. The strong magnetic field forces the electrons into a series of discrete, quantized Landau levels, and the perfect quantization of the Hall conductance is a consequence of the robust, topological nature of these quantum states. The discovery earned von Klitzing the Nobel Prize in Physics and opened up a new field of study, the field of topological states of matter. But the story does not end there. The quantum Hall effect, as beautiful as it is, requires the presence of a strong, external magnetic field. This is often inconvenient and limits its potential technological applications. But what if a material could be engineered to exhibit the quantum Hall effect without any external magnetic field? What if the material's own intrinsic properties could mimic the effect of a magnetic field? This is the essence of the quantum anomalous Hall effect. The anomalous here does not mean strange or unusual, but rather intrinsic or spontaneous. It is a quantum Hall effect that arises not from an external field, but from the material's own internal magnetic structure. The key ingredient for this phenomenon is the interplay between magnetism and topology. The materials that exhibit the quantum anomalous Hall effect are topological insulators, a new class of materials that have a very peculiar electronic structure. They are insulators in their bulk, meaning that electrons cannot flow through their interior, but their surfaces or edges are conducting. They have special, topologically protected electronic states that allow for the flow of current only along their boundaries. When such a topological insulator is made magnetic, for example, by doping it with a small amount of a magnetic element like chromium, something remarkable happens. The internal magnetization of the material acts on the electrons in the same way that an external magnetic field would. It breaks a fundamental symmetry of the system, time reversal symmetry. This symmetry states that the laws of physics should look the same if you were to run the movie of time backwards. A magnetic field, with its inherent directionality, breaks this symmetry. In a quantum anomalous Hall insulator, the intrinsic magnetization of the material breaks this symmetry. effectively creating an internal magnetic field that organizes the electrons into the same kind of quantized, edge-conducting states as in the standard quantum Hall effect. The result is a perfectly quantized Hall conductance, but with zero applied magnetic field. This is a profound and beautiful result. It shows how the abstract topological properties of a material's electronic structure can combine with the quantum mechanical property of electron spin to create a macroscopic quantum phenomenon. It is an example of emergence, where a complex collective behavior arises from the simple interactions of many individual components. The quantum anomalous Hall effect is not just a theoretical curiosity. It was first experimentally observed in 2013 in a thin film of a magnetic topological insulator. The experiments are incredibly challenging, as they require the precise fabrication of these exotic materials and measurements at extremely low temperatures. But the observation of a perfectly quantized Hall conductance at zero magnetic field was a stunning confirmation of the theoretical predictions. The discovery has ignited a new wave of research in condensed matter physics. Scientists are now searching for new materials that could exhibit the quantum anomalous Hall effect at higher, more practical temperatures. If such materials could be found, they could lead to a new generation of ultra-low-power electronic devices. The perfectly conducting edge states of a quantum anomalous Hall insulator are dissipationless. The electrons flow without any resistance, meaning no energy is lost as heat. This could be the basis for a new kind of topological electronics, with the potential for incredibly efficient and robust information processing. The quantum anomalous Hall effect is a beautiful example of how an anomaly, a breakdown of a classical symmetry, can be a source of new, rich, and technologically relevant physics. It is a story that connects the abstract beauty of topology, the strange rules of quantum mechanics, and the practical art of material science, a story that is still being written in laboratories around the world. The chiral anomaly is another profound and subtle example of a classical symmetry that is broken by the effects of quantum mechanics. It is a phenomenon that lies at the very heart of our understanding of the fundamental particles and forces, and it has deep implications for everything from the structure of the Standard Model to the origin of matter in the universe. To understand the chiral anomaly, we must first understand the concept of chirality. Chirality is a property of certain fundamental particles, like electrons and quarks, that is related to their handedness. Just as your left and right hands are mirror images of each other, but cannot be superimposed, these particles can exist in left-handed and right-handed versions. Chirality is closely related to a particle's spin, its intrinsic quantum mechanical angular momentum. For a massless particle, which travels at the speed of light, chirality is the same as its helicity, the projection of its spin onto its direction of motion. A left-handed particle spins like a left-handed corkscrew as it moves forward, while a right-handed particle spins like a right-handed one. In a classical field theory, if the underlying equations are symmetric with respect to left-handed and right-handed particles, then there should be a corresponding conservation law. The number of left-handed particles minus the number of right-handed particles, a quantity known as the axial charge, should be conserved in any interaction. This is the chiral symmetry of the classical theory. The chiral anomaly is the surprising discovery that this classical symmetry is broken at the quantum level. In certain quantum processes, the axial charge is not conserved. Left-handed particles can be turned into right-handed particles, and vice versa, in a way that violates the classical conservation law. This is not a failure of our theory. It is a deep and fundamental feature of the quantum world. The anomaly arises from the interaction of the chiral particles with the background gauge fields that mediate the fundamental forces. A gauge field, like the electromagnetic field, can be thought of as a kind of quantum ether that pervades all of space. And the quantum fluctuations of this field, the constant bubbling of virtual particles, can have a subtle and powerful effect on the chiral particles moving through it. One of the most intuitive ways to understand this is to consider the behavior of chiral particles in the presence of both an electric and a magnetic field that are parallel to each other. This configuration creates a kind of chiral pump. The magnetic field forces the charged chiral particles to move in circles into quantized Landau levels. The parallel electric field then acts on these particles, but it does so in a way that depends on their chirality. It can, for example, pump particles from a left-handed Landau level to a right-handed one, or vice versa, changing the net axial charge of the system. This process is a direct physical manifestation of the chiral anomaly. The anomaly is not just a theoretical curiosity. It has profound and far-reaching consequences. In the standard model of particle physics, the weak nuclear force, which is responsible for radioactive decay, is a chiral theory. It treats left-handed and right-handed particles completely differently. In fact, the weak force only ever interacts with left-handed particles and right-handed antiparticles. This is a manifest violation of parity, or mirror image symmetry, a discovery that shocked the physics world in the 1950s. The consistency of the standard model as a quantum field theory depends on a delicate and miraculous cancellation of various chiral anomalies. The contributions to the anomaly from the quarks and the leptons in each of the 3 generations of particles must precisely cancel each other out. If they did not, the theory would be mathematically inconsistent and would give nonsensical, infinite answers. The fact that they do cancel is a powerful, albeit circumstantial, piece of evidence for the structure of the standard model, and it provides a deep and mysterious connection between the seemingly disparate worlds of quarks and leptons. The chiral anomaly also plays a crucial role in our understanding of the strong nuclear force, the force that binds quarks together to form protons and neutrons. The theory of the strong force, quantum chromodynamics, has an approximate chiral symmetry that is broken by the anomaly. This anomaly is responsible for the decay of a neutral pion, a type of subatomic particle, into 2 photons. The observed rate of this decay is in perfect agreement with the prediction from the chiral anomaly, providing one of the most precise and beautiful experimental confirmations of this subtle quantum effect. But perhaps the most profound implication of the chiral anomaly is in the realm of cosmology. The universe we see today is made almost entirely of matter, with very little antimatter. This is a deep mystery. According to the standard Big Bang model, matter and antimatter should have been created in almost equal amounts in the early universe. As the universe cooled, they should have annihilated each other, leaving behind a universe filled only with a dilute sea of radiation. The fact that we are here, that matter exists at all, means that there must have been a slight asymmetry, a tiny excess of matter over antimatter. In the early universe, about 1 extra matter particle for every billion matter-antimatter pairs. The origin of this baryon asymmetry is one of the greatest unsolved problems in all of science. The Russian physicist Andrei Sakharov, in 1967, laid out the 3 necessary conditions for generating such an asymmetry. There must be processes that violate the conservation of baryon number. There must be a violation of C and CP symmetry, and there must be a departure from thermal equilibrium. The chiral anomaly, in the context of the electroweak theory, provides a mechanism for violating baryon number conservation at the high temperatures of the early universe. This process, known as Phaleron transitions, could have been responsible for converting a primordial lepton asymmetry into the observed baryon asymmetry. While this is just one of several competing theories for the origin of matter, it is a beautiful example of how a subtle, microscopic quantum anomaly can have a profound, macroscopic impact on the very existence of our cosmos. The chiral anomaly is a powerful and elegant reminder that the symmetries of our world are not always what they seem. It is a story of a classical beauty that is broken by the strange and wonderful logic of the quantum realm. A story of an asymmetry that may be the very reason we are here to tell the story at all. The conformal anomaly is another, and perhaps even more profound. Example of a classical symmetry that is broken by the subtle effects of quantum mechanics. It is a breakdown in the symmetry of scale, and it has deep and far-reaching implications for our understanding of quantum field theory, of quantum gravity, and of the very nature of space-time itself. Conformal symmetry is a powerful and elegant extension of scale invariance. A theory is scale invariant if its physical laws look the same at all scales of distance and energy. If you were to zoom in or out on a scale invariant system, you would see the same physics at play. Conformal symmetry is even more restrictive. It requires that the laws of physics remain the same, not just under a uniform rescaling of all distances, but under any conformal transformation. A transformation that preserves angles but can stretch and squeeze distances in a non-uniform way. In a classical field theory, many of our most fundamental theories, like Maxwell's theory of electromagnetism, are conformally invariant, at least in the absence of massive particles. This symmetry implies a number of powerful and beautiful consequences, including the conservation of a specific type of current, the dilatation current. The conformal anomaly is the surprising discovery that this beautiful classical symmetry is almost always broken at the quantum level. When we try to define a quantum field theory, we run into a problem with infinities. The interactions of particles with the virtual particles of the quantum vacuum lead to calculations that give infinite answers for physical quantities like mass and charge. To deal with this, physicists have developed a powerful and sophisticated set of techniques known as renormalization. Renormalization is a way of absorbing the infinities into a redefinition of a few key parameters of the theory, like the bare mass and charge of the particles. It is a remarkably successful procedure, and it is the foundation upon which the entire standard model of particle physics is built. But it comes at a price. The process of renormalization inevitably introduces a new, arbitrary energy scale into the theory, a renormalization scale, and the physical properties of the theory, like the strength of its forces, are now found to depend on this energy scale. A force that is strong at high energies can become weak at low energies, and vice versa. This running of the coupling constants is a fundamental feature of the quantum world, and it is a direct violation of scale invariance. The theory is no longer the same at all scales. The classical conformal symmetry has been broken by the quantum effects that are tamed by renormalization. This is the conformal anomaly. One of the most important consequences of the conformal anomaly is its effect on the stress-energy tensor, the mathematical object that describes the density and flow of energy and momentum in a physical system. In a classical, conformally invariant theory, the trace of the stress-energy tensor is zero. This is a mathematical statement of the fact that the theory has no intrinsic scale. But when the theory is quantized, the conformal anomaly gives a non-zero value to the trace of the stress-energy tensor. This trace anomaly is a direct physical manifestation of the breakdown of scale invariance. It is a measure of how much the quantum vacuum itself contributes to the energy and pressure of the system. The conformal anomaly has profound implications across a wide range of physics. In the theory of the strong nuclear force, quantum chromodynamics, the conformal anomaly is responsible for a large fraction of the mass of the protons and neutrons that make up the atoms in our bodies. The underlying theory of quarks and gluons is nearly massless, and classically, it would be nearly conformally invariant. But the conformal anomaly gives a huge contribution to the trace of the stress-energy tensor, which, in a sense, generates the mass of the composite particles like protons and neutrons. Most of your own mass is not from the Higgs mechanism. It is a direct, physical consequence of the conformal anomaly of QCD. It is the energy of the quantum vacuum, bound up inside the protons and neutrons of your body. In cosmology, the conformal anomaly plays a crucial role in our understanding of the early universe. The period of cosmic inflation is thought to have been driven by the energy of a quantum field in a nearly scale-invariant state. But the small deviations from perfect scale invariance, the small tilt in the spectrum of the primordial density fluctuations, are a direct consequence of the conformal anomaly. They are a measure of how the strength of the inflatons' interactions changed during the inflationary epoch. These tiny, anomalous deviations from perfect scale invariance are what gave rise to the seeds of all the structure in our universe. Without the conformal anomaly, the universe would have remained a perfectly smooth, homogeneous, and boring place. In the realm of theoretical physics, the conformal anomaly is a key concept in string theory. The consistency of string theory as a quantum theory of gravity depends on the cancellation of the conformal anomaly on the two-dimensional world sheet that the string traces out as it moves through space-time. This requirement of conformal invariance is an incredibly powerful constraint, and it is what determines the critical number of dimensions, 10, in the case of superstring theory in which the theory can consistently live. The conformal anomaly is, in a sense, the gatekeeper of string theory, the mathematical principle that ensures its consistency. And in condensed matter physics, the principles of conformal field theory, the study of quantum field theories that are conformally invariant, have become a powerful tool for describing the behavior of systems at a critical point. For example, a magnet at the precise temperature where it loses its magnetism. At these critical points, the system loses its intrinsic sense of scale, and its long-distance behavior is governed by the universal laws of a conformal field theory. The conformal anomaly is a subtle but profound concept. It is a story of a beautiful classical symmetry that is broken by the unavoidable and ultimately creative effects of the quantum world. It is a story that connects the mass of the protons in your body, the origin of the galaxies in the sky, and the very consistency of our most ambitious theories of fundamental reality. It is a reminder that the universe, at its deepest level, is a quantum universe. A universe where the simple, elegant symmetries of the classical world are often just a beautiful, but ultimately incomplete, approximation of a much richer, more subtle, and more dynamic reality. The gravitational anomaly is one of the most abstract, most subtle, and potentially most profound of all the quantum anomalies. It is a deep mathematical inconsistency that can arise when we try to combine the principles of quantum mechanics with Einstein's theory of general relativity, particularly in the presence of chiral fermions, the left-handed and right-handed particles that make up the matter in our universe. It is a puzzle that lies at the very heart of the quest for a theory of quantum gravity, and its resolution may hold the key to understanding some of the deepest secrets of the cosmos. To understand the gravitational anomaly, we must first appreciate the deep symmetries that underlie both quantum field theory and general relativity. The standard model of particle physics is built on the principle of gauge symmetry. This is a powerful, abstract symmetry that dictates the nature of the forces between particles. It requires that the laws of physics remain unchanged under a certain set of local, internal transformations of the quantum fields. The mathematical consistency of the theory, in particular the conservation of probability, depends crucially on this gauge symmetry being exact and unbroken. General relativity, on the other hand, is built on a different but equally powerful symmetry principle: diffeomorphism invariance, or general covariance. This is the principle that the laws of physics should be independent of the coordinate system we use to describe them. It is the mathematical embodiment of the principle of equivalence. The idea that gravity is not a force, but a manifestation of the curvature of space-time. The gravitational anomaly is a potential clash between these two fundamental symmetry principles. It can arise in a quantum field theory of chiral fermions coupled to gravity. The problem is that the quantum effects of the chiral fermions interacting with a curved gravitational background can sometimes conspire to break the gauge symmetry of the theory. This is a disaster. A theory with a gauge anomaly is mathematically inconsistent. It would predict probabilities that are not conserved, and it would give nonsensical, infinite answers. It is not a physically viable theory. For a long time, it was thought that the standard model of particle physics, with its specific and seemingly arbitrary collection of quarks and leptons, might suffer from such a gravitational anomaly. The theory contains chiral fermions, and it is coupled to gravity. It was a major theoretical worry. But in the 1980s, the physicists Luis Alvarez Gomez and Edward Witten performed a detailed and complex calculation and made a remarkable discovery. They found that, for the specific and peculiar collection of particles in the standard model, the potential contributions to the gravitational anomaly from all the different chiral fermions, the quarks and the leptons, miraculously and precisely cancel each other out. The standard model is, against all odds, free of any gravitational anomaly. This is a stunning and deeply mysterious result. It suggests a hidden and profound connection between the particle content of the universe and the consistency of quantum gravity. It is as if the universe knew that it had to have this specific and seemingly random collection of quarks and leptons in order to be a consistent quantum mechanical reality. The cancellation of the gravitational anomaly in the standard model is one of the strongest, albeit circumstantial, pieces of evidence we have for the deep, underlying unity of the fundamental laws of nature. It is a clue that the seemingly arbitrary structure of the standard model is not arbitrary at all, but is fixed by a deep requirement of quantum consistency. This principle of anomaly cancellation has become a powerful and guiding principle in the search for new physics beyond the standard model. Any new theory that seeks to extend the standard model, for example, by introducing new particles to explain dark matter, or new symmetries to unify the forces, must also be free of any gravitational or gauge anomalies. This is an incredibly powerful constraint, and it has been used to rule out a large number of otherwise plausible-looking theories. It is a kind of consistency check that any new theory must pass before it can even be considered a serious candidate for describing our universe. String theory, our most ambitious and well-developed candidate for a theory of quantum gravity, provides a beautiful and natural mechanism for anomaly cancellation. The theory, as we have seen, is only consistent in 10 spacetime dimensions. And in this 10-dimensional spacetime, the specific mathematical structure of the theory automatically ensures that all potential gravitational and gauge anomalies cancel out. This is one of the most remarkable and compelling features of the theory. It is as if the deep mathematical consistency of the theory itself dictates the particle content and the symmetries of the world, in a beautiful and profound realization of the bootstrap dream. The gravitational anomaly is a very abstract and technical subject, one that is far removed from the world of our everyday experience. But it is a subject of profound importance. It is a window into the deep mathematical structure of our universe. It is a story about the subtle and powerful ways in which the principles of quantum mechanics and general relativity constrain each other. And it is a story that has a beautiful and deeply satisfying, if still mysterious, ending. The universe we live in, with its specific and peculiar collection of fundamental particles, appears to be a universe that is exquisitely, and perhaps uniquely, designed to be free of the mathematical inconsistencies that would have made its own quantum existence impossible. It is a universe that is, in the deepest sense, self-consistent, the gravitational anomaly. And its miraculous cancellation in the Standard Model is a powerful whisper from the cosmos, a hint that beneath the apparent complexity and randomness of the world, there lies a deep, hidden, and beautiful mathematical order. The gauge anomaly, like the gravitational anomaly, is a subtle but crucial aspect of quantum field theory that deals with the consistency and integrity of the symmetries that govern the fundamental forces of nature. While the gravitational anomaly concerns the consistency of a theory when coupled to the external, classical field of gravity, the gauge anomaly concerns the internal, quantum consistency of the gauge symmetries themselves. As we have seen, the Standard Model of particle physics is a gauge theory, GE. This means that its structure is dictated by a principle of local gauge symmetry. This is the requirement that the laws of physics should remain the same even if we make different, independent transformations on the quantum fields at different points in space-time. To maintain this symmetry, the theory must include gauge fields, which give rise to the force-carrying particles, the gauge bosons, like the photon, the W and Z bosons, and the gluons. The gauge symmetry is not just an aesthetic principle, it is the very foundation of the theory's mathematical consistency. It is what guarantees the conservation of fundamental quantities like electric charge, and it is what ensures that the theory is renormalizable, meaning its predictions are free from the nonsensical. Infinite answers that can plague quantum field theory calculations. A gauge anomaly is a situation where this fundamental, classical gauge symmetry is broken by quantum effects. This is a much more serious problem than the breaking of a global symmetry, like the chiral symmetry we discussed earlier. The breaking of a global symmetry can lead to interesting and observable physical phenomena, like the decay of the neutral pion. But the breaking of a local gauge symmetry is a sign that the theory is fundamentally inconsistent. It is a mathematical sickness, a sign that the theory is not a valid description of physical reality. The problem arises, once again, from the subtle effects of chiral fermions. In a gauge theory with chiral fermions, the quantum loop diagrams, which describe the interactions of the fermions with the virtual particles of the vacuum, can sometimes conspire to produce a result that is not gauge invariant. This would be a disaster. It would mean that the theory is not renormalizable, that it does not conserve charge, and that it is not a physically sensible theory. For the Standard Model to be a consistent theory of our universe, all of its potential gauge anomalies must cancel out. And, in another beautiful and mysterious miracle of mathematics, they do. The Standard Model has a very specific and intricate structure. It has a gauge symmetry group known as SU, X, SU, XU, and it has a very specific collection of chiral quarks and leptons arranged in 3, seemingly redundant, generations. When physicists calculate the potential contributions to the gauge anomalies from all of these different particles and forces, they find that, for each of the many possible anomalies, the contributions from the quarks and the leptons, with their specific and peculiar charges, cancel each other out with exquisite precision. For example, the contributions from the left-handed quarks in a given generation precisely cancel the contributions from the left-handed leptons. This is a highly non-trivial and deeply profound result. It suggests that the seemingly arbitrary structure of the Standard Model, the specific number of colors for quarks, the specific charges of the leptons, the existence of exactly 3 generations is not arbitrary at all. It is a structure that is tightly constrained, and perhaps uniquely determined by the requirement of quantum consistency, by the requirement that the theory be free of any mathematical sickness. This principle of anomaly cancellation has become a powerful and guiding principle in the search for physics beyond the Standard Model. Any proposed grand unified theory, which seeks to unify the strong, weak, and electromagnetic forces into a single, larger gauge group, must also be free of any gauge anomalies. This is an incredibly restrictive constraint, and it has been used to rule out many otherwise attractive-looking gut models. The fact that some of the most elegant and compelling gut models, like the one based on the gauge group SO, automatically and naturally satisfy these anomaly cancellation conditions is seen by many as a strong hint that they may be on the right track. The gauge anomaly, boy, then is a beautiful example of the deep and subtle interplay between symmetry, quantum mechanics, and mathematical consistency. It is a story of a potential fatal flaw in our theories that is miraculously and beautifully avoided by the specific and seemingly peculiar structure of the world we live in. It is a powerful piece of circumstantial evidence that the universe is not a random collection of particles and forces, but is a deep, coherent, and exquisitely self-consistent mathematical structure. It is a whisper from the cosmos that there is a deep and hidden reason for the way things are. A reason that is written not in the language of our everyday experience, but in the abstract, elegant, and powerful language of symmetry and quantum field theory. The gauge anomaly, in its absence, is one of the most profound and beautiful clues we have in our ongoing quest to read the mind of God. The Weyl anomaly, often used interchangeably with the conformal anomaly we've already explored, is a specific and crucial manifestation of the breakdown of scale symmetry in quantum field theory, particularly when the theory is formulated on a curved space-time background. While the conformal anomaly speaks generally about the breakdown of scale invariance, the Weyl anomaly specifically refers to the non-invariance of a theory under Weyl transformations, local position-dependent rescalings of the space-time metric. It's a subtle but important distinction that lies at the heart of our attempts to understand quantum gravity. In classical general relativity, the theory is diffeomorphism invariant, meaning the laws of physics are independent of our choice of coordinates. However, it is not, in general, Weyl invariant. A change in the local scale, a stretching or shrinking of our rulers and clocks that varies from point to point, would change the physics. But in a classical theory of massless particles, like Maxwell's theory of electromagnetism, the theory is Weyl invariant. The physics of massless particles does not depend on an absolute scale of distance. This beautiful classical symmetry, however, is broken at the quantum level. The quantum fluctuations of the vacuum, as we have seen, introduce a fundamental scale into the theory through the process of renormalization. This breakdown of classical Weyl symmetry in a quantum theory is the Weyl anomaly. The anomaly manifests itself as a specific, non-zero contribution to the trace of the stress-energy tensor, a contribution that is proportional to the curvature of the space-time background. It is a direct measure of how much the quantum vacuum responds to the geometry of the space it inhabits. This is a profound and beautiful result. It tells us that the quantum vacuum is not a passive, inert background. It is a dynamic, physical medium that can be polarized and energized by the very curvature of space-time. The Weyl anomaly has deep and far-reaching implications. In the context of the early universe, it plays a crucial role in the process of reheating after inflation. The rapid, exponential expansion of inflation dilutes all the pre-existing matter and radiation, leaving behind a cold, empty universe filled only with the energy of the inflaton field. As the inflaton field decays, its energy is converted into a hot plasma of standard model particles. The Weyl anomaly is a key part of this process. The changing curvature of space-time during the end of inflation can, through the Weyl anomaly, directly create particles from the quantum vacuum, a process known as gravitational particle production. It is a mechanism by which the energy of the expanding universe itself is converted into the matter and radiation that fills our cosmos. The Weyl anomaly is also a central and crucial concept in string theory. String theory, at its core, is a two-dimensional quantum field theory living on the world sheet that the string sweeps out as it moves through space-time. The consistency of the theory, in particular, the absence of unphysical, ghost states with negative probability, depends on this two-dimensional theory being conformally invariant, which means its Weyl anomaly must vanish. This is an incredibly powerful constraint. It turns out that the Weyl anomaly on the string worldsheet only vanishes if the background spacetime in which the string is moving satisfies Einstein's equations of general relativity. And if the number of spacetime dimensions is exactly 26 or 10, this is a truly remarkable result. It means that the dynamics of spacetime, the laws of gravity, are not an input into string theory. They are an output. Einstein's general relativity emerges as a necessary condition for the quantum consistency of the theory. The requirement that the Weyl anomaly vanishes is what bootstraps the theory into a consistent theory of quantum gravity. It is one of the most beautiful and compelling arguments in favor of string theory, a hint that it is not just another quantum field theory, but a deep and perhaps unique framework for unifying all the fundamental principles of nature. The Weyl anomaly is a subtle, technical, and often overlooked aspect of quantum field theory, but it is a concept of profound beauty and power. It is a window into the deep, dynamic relationship between the quantum vacuum and the geometry of space-time. It is a key ingredient in our story of the early universe, and it is the central, organizing principle that ensures the mathematical consistency of our most ambitious and promising theory of quantum gravity. It is a beautiful example of how a broken symmetry, an anomaly, is not a flaw, but a source of deep physical insight, a clue that points us towards a richer, more unified and more beautiful understanding of the cosmos. The landscape of quantum anomalies, with its subtle and often counterintuitive breakdowns of classical symmetries, presents a profound and ongoing challenge to our understanding of the universe. It is a realm where our most cherished and fundamental principles, the conservation of charge, the symmetry of scale, the very consistency of our physical laws, are tested and found to be more fragile, more conditional, and more mysterious than we ever thought. From the dissipationless edge currents of the quantum anomalous Hall effect to the matter-creating potential of the chiral anomaly. From the mass-generating power of the conformal anomaly to the consistency-enforcing constraints of the gauge and gravitational anomalies, we have seen that the universe, at its quantum core, is a place of deep and beautiful paradox. These anomalies are not imperfections in the cosmic design. They are the very source of its richness, its complexity, and its capacity for creative evolution. The universe we inhabit, a universe of stable matter, of distinct forces, of complex structures, of life itself, is a universe that is only possible because of these subtle and beautiful breakings of symmetry. A perfectly symmetric universe would be a perfectly boring universe, a sterile and featureless void. It is the anomalies, the glitches in the classical code, that allow for the emergence of the new, the unexpected, and the beautiful. The study of these anomalies has been, and will continue to be, a powerful engine of scientific progress. They have guided us in the construction of the standard model of particle physics, with its strange and beautiful pattern of anomaly cancellations. They are now guiding us in our search for a theory of everything, providing the crucial consistency checks that any new theory of quantum gravity must pass. And they are inspiring a new generation of technologies, from the dissipationless electronics of the topological age to the powerful transformative potential of quantum computing. But beyond their role in science and technology, the quantum anomalies offer us a deep philosophical and even spiritual lesson. They teach us a lesson in humility, a reminder that our classical, common-sense understanding of the world is a limited and provisional one, a useful approximation that breaks down in the face of a deeper, stranger, and more mysterious reality. They invite us to embrace the paradox, to hold the tension between the expected and the actual, between the symmetry and its breaking. They show us that the universe is not a static, finished, and perfectly predictable machine, but a dynamic, evolving, and endlessly creative process. A process that is constantly surprising us, challenging us, and inviting us into a deeper and more intimate relationship with its own unfolding mystery. The quantum world is not a world of solid facts, but a world of vibrant possibilities, a world where the very act of observation helps to shape the reality we perceive. And as we continue to probe this strange and beautiful realm, with our powerful new instruments and our ever more sophisticated theories, we are not just uncovering the secrets of the cosmos, we are also uncovering the secrets of ourselves. We are discovering that we are not separate from this quantum drama, but are an integral part of it. We are the observers whose gaze helps to collapse the wave function of the universe. We are the conscious beings whose existence is a testament to the beautiful and miraculous asymmetry of the cosmos. And as you lie on the threshold of sleep, as your own, classical consciousness begins to dissolve into the quantum, dreamlike sea of the unconscious. You can feel a sense of participation in this grand cosmic story. The anomalies of the universe are not just out there, in the world of particles and fields, they are also in here, in the deep, paradoxical, and endlessly creative mystery of our own human soul. Imagine waking up one day to a world that feels both deeply familiar and utterly strange. A reality where the solid ground beneath your feet and the steady forward march of time are revealed to be just the tip of a cosmic iceberg. What if everything you see, every choice you make, and every fleeting moment you experience are not isolated events, but fragments of a much grander, more intricate, and largely unseen structure? This is the world we are about to explore together, a universe not confined to the familiar three dimensions of our senses, but one that stretches into realms that defy our intuition and challenge our imagination. At first glance, our lives seem straightforward enough. We exist in a space defined by three coordinates. We can move left and right, up and down, forward and backward. And we are carried along by a fourth dimension, the relentless current of time, which pushes us ever onward from the past, through the present, and into an unknown future. But as science has delved deeper into the nature of reality, it has uncovered a set of rules that seem to border on magic, a subatomic realm where the common sense of our macroscopic world dissolves into a shimmering sea of probability and potential. This is the world of quantum physics, a world where particles can be in many places at once, where the very act of observation seems to shape the reality being observed, and where the linear flow of time itself may be nothing more than a stubborn illusion. To begin this journey, let us start with the simplest of concepts, a single, dimensionless point. It has no length, no width, no depth. It is a pure, abstract location. Now, connect two such points, and you have a line. The first dimension, a world of pure length. Add a second direction, perpendicular to the first, and you create a plane, a two-dimensional world of length and width, like the surface of a sheet of paper. This is the world of geometry, of squares, circles, and triangles. And if you take this two-dimensional plane and fold it, pulling it up into a third direction, you create the three-dimensional space that we call home, a world of solid objects with length, width, and height. This progression seems intuitive enough, but what happens if we continue this pattern? What lies beyond the familiar three dimensions of our physical world? This is where our journey into the strange and beautiful landscape of modern theoretical physics truly begins. The first step beyond our spatial reality is into the fourth dimension, a concept that is most commonly, and perhaps most intuitively, understood as time. In this picture, time is not just a fleeting, intangible flow, but a dimension akin to space. Our entire existence, from the moment of our birth to the moment of our death, can be visualized as a single, four-dimensional object, a world line or a space-time worm snaking its way through the unified fabric of space-time. Your past, your present, and your future all exist simultaneously in this block universe, and your consciousness is simply a spotlight, a point of awareness, moving along this pre-existing, four-dimensional reality. But what if this single, linear timeline is not the only one? What if every choice we make, every random, quantum event in the universe, causes reality to split, to branch off into a new, parallel timeline? This is the gateway to the fifth dimension. The fifth dimension is not a new direction in space, but a new direction in the landscape of possibility. It is the dimension that contains all the alternate histories, all the what-ifs, all the different paths that our universe could have taken, branching out from every moment of choice. There is a timeline where you took that job, and a timeline where you did not. A timeline where the dinosaurs never went extinct, and a timeline where they evolved into intelligent, sentient beings. The fifth dimension is the space of these branching possibilities, a vast, ever-growing tree of alternate realities. As we ascend further up this dimensional ladder, the concepts become increasingly abstract, moving from the realm of physics into a space that feels closer to metaphysics. The sixth dimension allows us to not just conceive of these branching timelines, but to fold the space of possibilities itself. It is a dimension that would allow for a kind of shortcut between different, seemingly distant branches of the multiverse. It is the plane that contains all the possible histories that could have arisen from the same initial conditions of our Big Bang. A complete, phase space of our specific kind of universe. The seventh dimension marks an even more profound leap. It is the dimension that contains the set of all possible universes that could have started with different initial conditions. This is the realm of universes with different physical laws, different fundamental constants, different numbers of spatial dimensions. It is a library of all possible cosmic beginnings, each one giving rise to its own, unique, six-dimensional tree of possibilities. The eighth dimension is the plane that contains all of these different cosmic libraries, allowing for a comparison, a branching between these fundamentally different kinds of realities. The ninth dimension takes this to its logical extreme. It is the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the ultimate ensemble, the set of all possible universes. And finally, we arrive at the 10th dimension, in the conceptual framework of string theory, the leading candidate for a unified theory of everything. The universe has 10 spatial dimensions and one of time. The extra 6 dimensions beyond our familiar 3 are thought to be compactified, curled up into a tiny, complex geometrical shape at every point in our space. But in a more conceptual, hierarchical sense, the 10th dimension can be thought of as the ultimate point of origin, a dimensionless point of pure potential from which all the lower dimensions, all the possibilities, all the universes emerge. It is the everythingness that contains all possible realities, a concept so vast, so all-encompassing, that it transcends our ability to visualize or even fully comprehend. This journey through the dimensions is not just a mathematical game. It is a profound and humbling exploration of the potential richness and complexity of reality. It suggests that the universe we experience, with its familiar 3 dimensions and its steady forward-moving time, may be just a single, thin slice of a much grander, multidimensional, and endlessly fascinating cosmic structure, a structure whose deepest secrets are hidden in the unseen. and perhaps unknowable. Dimensions that lie just beyond the horizon of our perception. The strange and counterintuitive world of quantum mechanics provides another, equally profound, challenge to our classical common-sense understanding of reality. At the subatomic level, the very fabric of existence seems to be woven from threads of uncertainty, of probability, and of a deep participatory relationship between the observer and the observed. The solid, definite world of our everyday experience dissolves into a shimmering, ghostly sea of potential. The fundamental constituents of our universe, the particles that make up every atom in our bodies, are not solid, billiard ball-like entities. They exist as waves of probability, their properties not fixed and definite, but existing in a superposition of all possible states at once until the moment of measurement. And it is this act of measurement, of observation, that seems to be the magical ingredient that collapses this wave of potential into a single, definite reality. This raises one of the most profound and unsettling questions in all of science. Are we, in some sense, creating reality by the very act of observing it? If a particle does not have a definite position until we look at it, then what does it mean to say that it exists? Before our observation, this is a question that has divided physicists for a century, leading to a host of different and often bizarre interpretations of the quantum world. Some physicists take a pragmatic view, arguing that these quantum effects, while real and measurable in the subatomic realm, are confined to that realm, a process known as decoherence. The constant interaction of a quantum system with its environment is thought to rapidly destroy the delicate superposition of macroscopic objects, ensuring that the classical world of our everyday experience remains stable and predictable. The quantum possibilities are still there, but they have faded into the background, their interference effects washed out by the noise of the environment, leaving us with a single, coherent, classical reality. But others have been drawn to more radical conclusions. The many worlds interpretation, for example, proposes that the wave function never truly collapses. Instead, every quantum measurement causes the entire universe to split into multiple, parallel branches, with each branch corresponding to one of the possible outcomes. In this view, we are not collapsing reality. Our observation is simply entangling us with one particular branch of a vast, ever-growing multiverse. We are not creating a single reality. We are choosing our path through an infinite, pre-existing tapestry of all possible realities. This is like tuning a radio. All the other stations are still broadcasting, but we are only experiencing the one we have locked onto. This line of thought leads to even deeper and more perplexing questions. If observation is the key to actualizing reality, then who or what was the first observer? What existed before the emergence of life, of consciousness, in the universe? Did the cosmos exist for billions of years as an uncollapsed, ghostly sea of pure potential, waiting for a conscious mind to come along and give it form? Or was there some other, more fundamental form of observation at play? A cosmic observer that has been collapsing the wave function since the very beginning. The relationship between observation and the flow of time is another area of deep mystery and speculation. We experience time as a relentless one-way arrow, moving from a fixed past to an open future. But what if this arrow of time is not a fundamental property of the universe, but an illusion, a story that our consciousness constructs? What if, at a deeper, multidimensional level, all of time past, present, and future exists simultaneously? In this block universe picture, the act of observation at a single point in time, the present moment, could be what creates the appearance of a consistent historical past leading up to that moment. It is a radical idea, The notion that our present awareness could, in a sense, retroactively create the billions of years of cosmic history that we observe. It is as if, from the ultimate vantage point of the 10th dimension, a single choice, a single act of observation, collapses not just a present state, but an entire, consistent, four-dimensional space-time history. This is a concept that strains the limits of our language and our logic, but it is one that is being seriously explored at the frontiers of theoretical physics. The very terms we use, observer, measurement, consciousness, are laden with philosophical baggage. For some, the role of the observer is synonymous with the role of a creator, or even of God. The idea that a divine cosmic mind is constantly observing and therefore creating. The universe is a powerful and enduring one that is found in many of the world's spiritual traditions. From a scientific perspective, this is not a testable hypothesis. But the parallels between these ancient metaphysical ideas and the strange, participatory reality suggested by quantum mechanics are undeniably fascinating. They suggest that we may be on the verge of a new synthesis, a new understanding of reality that can bridge the long-standing gap between the inner world of subjective experience and the outer world of objective science. What is clear is that the simple, mechanistic picture of a universe that exists out there, independent of our own minds, is no longer tenable. We are not separate from the reality we observe. We are deeply and mysteriously intertwined with it. The act of attention, of awareness, is not a passive process. It is a creative, world-shaping force. And the question of how far this power extends, of what other hidden layers of reality might be accessible to a new and more refined form of consciousness, is perhaps the most exciting and profound adventure that humanity has ever embarked upon. The familiar intuitive experience of time as a steady, unidirectional flow, a relentless arrow pointing from the past, through the present, and into the future, is one of the most fundamental, and yet most mysterious, aspects of our reality. The British astrophysicist Sir Arthur Eddington, in 1928, coined the evocative phrase, the arrow of time, to capture this powerful one-way nature of our temporal experience. We see glasses break, but we never see them spontaneously reassemble. We remember yesterday, but we have no direct knowledge of tomorrow. This seems so obvious, so deeply woven into the fabric of our existence, that we rarely stop to question it. And yet, when we look at the most fundamental laws of physics, this arrow of time is strangely absent. The equations of Newtonian mechanics, of Maxwell's electromagnetism, and even of Einstein's theory of relativity, are all time reversal symmetric. They work just as well for a process running forwards in time as for one running backwards. The laws themselves do not distinguish between the past and the future. So, if the fundamental laws are symmetric, where does the manifest asymmetry of our world come from? Why do we experience time as a one-way street? The standard answer lies in the second law of thermodynamics, which states that the total entropy or disorder of a closed system always increases over time. The universe began in a state of incredibly low entropy, a highly ordered and uniform state, and it has been evolving towards a state of higher entropy ever since. This provides a thermodynamic arrow of time, a statistical directionality that explains why systems in our universe tend to move from order to disorder. But this just pushes the question back a step. Why was the early universe in such a special, low entropy state to begin with? This is one of the deepest unsolved problems in all of cosmology. But what if there is another, even more profound, layer to this mystery? What if the arrow of time is not just a property of the universe, but is intimately linked to the nature of life and consciousness itself? Consider a simple chemical reaction, where two molecules, A and B, combine to form a new molecule, C. We perceive this as a forward-moving process, but the underlying physical laws would allow, in principle, for the reverse reaction, for C to spontaneously break apart into A and B. In our observed reality, however, the forward reaction is overwhelmingly dominant. Why, some have speculated that the very emergence of life, the self-organizing processes that arose from the primordial soup billions of years ago, may have somehow selected a preferred direction of time. Perhaps the complex information processing systems that we call life can only maintain their delicate, low-entropy state by surfing the universal wave of increasing entropy. Life, in this view, is a process that creates local pockets of order by exporting disorder to its environment, a process that is fundamentally tied to the thermodynamic arrow of time. But this leads to a fascinating and deeply speculative thought experiment. If the emergence of life is somehow linked to the arrow of time, could there be other forms of life in other corners of the cosmos, or perhaps even in a parallel universe, that have evolved in a universe with a reversed arrow of time? What would such a reverse time life form be like? To us, its actions would appear to be a bizarre reversal of causality. Its effects would precede its causes. A shattered cup would reassemble in its hands, and then it would place the whole cup on the table. It would be born old and die young. Communication with such a being would be a logical impossibility, a dizzying paradox of crossed causalities. The science fiction trope of a backward-flowing timeline provides a powerful way to explore these conceptual puzzles. Imagine an alien civilization whose history unfolds in reverse relative to our own. Their arrival on Earth in our year 3000 would be, from their perspective, the beginning of their historical interaction with us, their subsequent conquest of the planet, which from our perspective would look like a slow, inexplicable retreat, would be, for them, a story of glorious expansion. Who, in this paradoxical encounter, is the victor? The question itself dissolves into meaninglessness. The very framework of a shared, linear narrative breaks down. While this is a highly speculative scenario, it is one that is not entirely disconnected from the frontiers of theoretical physics. The idea of a mirror universe, a universe where the laws of physics are a mirror image of our own, including a reversed arrow of time, has been seriously proposed as a potential solution to some of the puzzles of cosmology, such as the nature of dark matter. In this picture, our universe and this mirror universe could have been born together in the Big Bang, moving in opposite directions in time from a common origin. The ultimate nature of time may be even stranger than these scenarios suggest. The block universe view, which arises from Einstein's theory of relativity, suggests that all of time past, present, and future exists simultaneously as a single, four-dimensional space-time manifold. In this view, the flow of time is an illusion, a product of our consciousness moving through this pre-existing static block. If this is the case, then the arrow of time is not a property of the universe itself, but a property of our perception. Perhaps our brains are wired in such a way that we can only process information sequentially, creating the subjective experience of a flowing now that moves from a remembered past to an anticipated future. But what if this is just one possible mode of consciousness? Could there be other forms of awareness that could perceive the block universe in a different way, that could access the past and the future with the same ease that we access different locations in space? And what if, at an even deeper, multidimensional level, the very concept of a single timeline, whether forward or backward, is an oversimplification? In the higher dimensional reality suggested by some theories, our entire four-dimensional spacetime could be just one slice of a much larger, more complex structure, a structure that contains all possible timelines, all possible histories, all at once. From this ultimate atemporal perspective, the distinction between forward and backward, between cause and effect, might cease to have any meaning. It would be like looking at a complex, woven tapestry. From the perspective of a single thread, there is a clear, linear path. But from the perspective of the whole, there is only the intricate, beautiful, and timeless pattern of the weave itself. The arrow of time, which feels so fundamental and unshakable to us, may be just a local, emergent, and perhaps even illusory feature of our particular corner of a much grander and much stranger cosmic reality. Imagine a reality where every decision you have ever made, every path you have ever taken, and every possibility you have ever considered all exist simultaneously, woven into the vast, multi-dimensional fabric of existence. This is a universe where the simple, binary logic of yes or no, of this or that, becomes the fundamental building block of an infinitely complex and beautiful cosmic structure. This binary viewpoint is not a formal scientific theory, but a powerful conceptual framework, a lens through which we can begin to grasp the mind-bending implications of modern physics, from the quantum world to the highest, most abstract dimensions of reality. It is a way of seeing the universe not as a collection of things, but as a cascade of choices, a story written in the simple yet profound language of binary decisions. At its heart, this viewpoint suggests that the universe, in its most fundamental state, is a realm of pure, unmanifest potential. The Big Bang, the moment we perceive as the beginning of our cosmos, can be reimagined not as a random, chaotic explosion, but as the first great binary toggle. The first yes in an infinite sea of no. It is the moment when the universe chose existence over non-existence, something over nothing. This single, primordial choice unleashed a cascade of subsequent bifurcations, a torrent of binary decisions that have shaped the evolution of our reality ever since. The theory of cosmic inflation, with its period of hyper-accelerated expansion in the first fraction of a second, aligns beautifully with this picture. It can be seen as the rapid, exponential unfolding of the possibilities contained within that first binary moment, the unfurling of the cosmic blueprint that was encoded in that initial choice. From this ultimate, atemporal perspective, the very concept of a before the Big Bang is transformed. It is not a question of what existed in a preceding time, but of what existed in a state of uncollapsed, pre-binary potential. It is a journey backward not in time, but into a realm of pure, undifferentiated indeterminacy. A shimmering fog of possibility waiting for the first creative act of distinction, the first yes or no, to give it form. This binary, decision-based framework is not just a feature of the cosmos. It is a fundamental feature of our scientific inquiry itself. The history of science is a history of branching paths, of competing interpretations of the same data. Isaac Newton's laws of motion and gravity provided a powerful and precise framework that reigned for centuries. But when Albert Einstein introduced his theory of general relativity, which described gravity not as a force, but as the curvature of a dynamic spacetime, he did not render Newton's laws wrong. He offered a new, deeper, and more comprehensive interpretation of the same phenomena. Newton's theory became a collapsed state, a highly accurate approximation that works perfectly well in the low-gravity, low-velocity regime of our everyday experience. Einstein's theory represents a different branch of the possibility space, a different way of looking at the same cosmic rhythm. The two theories are not mutually exclusive in a simple, binary sense. They are two different and complementary layers of a single, multi-layered truth. We see the same pattern in the development of our understanding of matter. The classical picture of solid, point-like particles gave way to the quantum picture of wave-particle duality. And string theory, in its most ambitious form, seeks to unify these different pictures by proposing that the fundamental constituents of reality are neither particles nor waves, but tiny, vibrating strings of energy. Each of these theoretical shifts is not a negation of what came before, but an expansion of the possibility space, a new and more nuanced way of interpreting the fundamental binary choices that seem to govern the cosmos. This leads us to a profound and unsettling question about our own place in this branching. Decision-based reality. If every quantum event, every choice, creates a new timeline, a new branch of the multiverse, then where are we? The many worlds interpretation of quantum mechanics suggests that we are on all the branches at once, that there are an infinite number of us, each living out a different reality. But our subjective experience is one of a single, continuous, and coherent life. Why do we perceive only this one particular path through the infinite, binary forest of possibilities? The answer may lie in the nature of consciousness itself. Perhaps our consciousness, our point of awareness, is the very thing that navigates this multidimensional landscape, collapsing the wave function of our own experience into a single, linear narrative. We are the thread that is being woven through the tapestry, and the path we take is the story of our lives. This brings us to the ultimate paradox, the tension between free will and determinism. If all possible outcomes exist somewhere in the multiverse, then what is the meaning of our choices? The binary viewpoint offers a fascinating, if speculative, resolution. It suggests that while all paths may exist in a state of potential, our consciousness, through the act of choice, is what makes a particular path real for us. The universe, in this picture, is deterministic in that all possibilities are governed by the underlying mathematical laws of the wave function. But we experience free will because our consciousness is the agent that chooses which of these deterministic paths to actualize, to experience as our reality. We are both the characters in a pre-written play, and the audience that, by its very attention, brings a particular performance to life. This idea finds a powerful fictional expression in the works of authors like Philip K. Dick and Jorge Luis Borges, who constantly explore the nature of reality, of alternate histories, and of the power of the mind to shape its own experience. It is a vision of the universe that is both deeply mechanistic and profoundly magical. A universe where the rigid laws of physics and the creative freedom of consciousness are two sides of the same, fundamental, binary coin. The binary viewpoint is not a scientific theory in the traditional sense. It is a conceptual tool, a way of thinking, a new lens through which to view the mysteries of the cosmos. It invites us to see the universe not as a static, predetermined machine, but as a dynamic, interactive, and endlessly creative process, a process of constant becoming, a story that is being written, moment by moment, choice by choice, in the simple, yet infinitely profound, language of yes and no. And as we stand at the crossroads of our own lives, facing the infinite, branching possibilities of our own future, we can take some comfort in the idea that we are not just making a choice in the universe, but that our very choice is an act of creation, an act that helps to shape the very fabric of reality itself. At the heart of our existence lies a paradox that is both deeply personal and profoundly cosmic. The universe we inhabit appears to be exquisitely and improbably fine-tuned for the existence of life. From the strength of the force of gravity to the precise mass of the proton, the fundamental constants of nature seem to have been set to just the right values to allow for the formation of stable atoms, of long-lived stars, of planets with complex chemistry, and ultimately of conscious, questioning beings like ourselves. If any of these values were even slightly different, the universe would be a sterile and barren place. This apparent fine-tuning has led to a great deal of debate among scientists and philosophers. For some, it is the most compelling evidence we have for the existence of a divine creator, a guiding hand that has purposefully designed the cosmos with us in mind. But for many cosmologists, there is a more natural, if no less astonishing, explanation, the anthropic principle. In its simplest form, the anthropic principle is a statement of selection bias. It says that the reason we observe a universe that is hospitable to life is because we could not, by definition, observe one that was not. We are here to ask the question precisely because our universe is one of the rare, life-friendly ones. This principle gains its full explanatory power when it is combined with the idea of a multiverse. If there are countless, perhaps an infinite number of other universes, each with its own randomly assigned set of physical laws and constants, then it is no longer a surprise that at least one of them, by sheer chance, would have the right conditions for life. We are simply the winners of a cosmic lottery of unimaginable proportions. It is a powerful and elegant explanation, but it is one that relies on the existence of a vast and perhaps forever unobservable ensemble of other realities. The anthropic principle, in this context, becomes a kind of statistical inevitability. But it also raises a host of new and perplexing questions. If every possible outcome of every quantum event is realized in a separate branch of the multiverse, as the many worlds interpretation suggests, then what is the status of these other realities? Are they as real as our own? And why do we experience only this one, single, coherent timeline? The complexity of our own existence provides a powerful, if metaphorical, parallel to this cosmic puzzle. The human eye, for example, is a marvel of biological engineering, an instrument of such intricate and perfectly coordinated complexity that it can seem, at first glance, to be the product of intelligent design. How could such a thing have evolved through a series of random, unguided mutations? The answer, of course, is the power of natural selection acting over immense geological timescales. But the anthropic principle offers a different kind of explanation, a different way of looking at the same improbability. It suggests that in the vast, multidimensional possibility space of all possible biological forms, the existence of a complex, image-forming eye is not improbable at all. It is a necessary condition for the emergence of an observer who can look up at the stars and wonder about the nature of reality. The eye and the universe it observes are part of a self-consistent, participatory loop. This brings us back to the binary viewpoint, the idea that reality is a cascade of choices. The Big Bang itself can be seen as the first great binary toggle, the choice of existence over non-existence. The subsequent period of cosmic inflation was the rapid unfolding of the possibilities contained within that initial choice. And every subsequent event, from the formation of the first atom to the evolution of the first living cell, can be seen as a further collapse of the universal wave function, a further selection of one path from an infinite, branching tree of possibilities. Our universe, with its specific set of laws and its capacity for life, is the result of a particular and very long sequence of yes-no decisions. The anthropic principle, in this light, is not just a statement about our universe. It is a statement about the nature of observation itself. Our consciousness, our ability to observe and to ask questions, is what collapses the vast, superpositional reality of the multiverse into the single, experienced reality of our timeline. We are not just living in a universe that is fine-tuned for us. We are, in a very real sense, the tuners. This is a radical and deeply challenging idea, one that places consciousness at the very center of the cosmic story. It suggests that the line between the subjective and the objective, between the mind and the world, is not as clear as we once thought. But what about the other timelines? The other universes where the cosmic dice roll came up differently? What about the universe where the laws of physics are slightly different, where JFK's assassination was thwarted, where a different sperm fertilized the egg that became you in the many worlds picture? These realities are all equally real, branching off from our own at every moment of choice. They are the might-have-beens that are somewhere else, the what-ises. We can never access them. We can never know them directly. But the anthropic principle, combined with the multiverse, suggests that they are an integral part of the grand cosmic tapestry. Our reality is just one thread in this infinite weave. This is a vision that can be both humbling and liberating. It is humbling because it removes our own personal story from the center of creation. But it is also liberating because it opens up an infinite space for possibility, for creativity, for the endless, beautiful, and sometimes tragic unfolding of all that could ever be. And as we stand on the precipice of our own choices, we can do so with a new and profound sense of the weight and the wonder of our own creative participation in the grand and perhaps infinite drama of the cosmos. The concept of time travel, long a staple of science fiction, becomes a far more complex and philosophically charged endeavor when viewed through the lens of a multidimensional, branching reality. The classic paradoxes of time travel, like the famous grandfather paradox, are all predicated on the assumption of a single, linear, and mutable timeline. If you travel back in time and prevent your own grandfather from meeting your grandmother, you create a logical contradiction. If you were never born, then you could not have traveled back in time to do the deed in the first place. But in a universe governed by the principles of quantum mechanics and higher dimensions, the story is not so simple. The many worlds interpretation of quantum mechanics offers a clean, if mind-bending, solution to these paradoxes. When you travel back in time and alter a past event, you are not changing your own history. You are simply creating a new branch of the multiverse, a new parallel timeline. In this new timeline, you were indeed never born. But in your original timeline, the one you departed from, your journey into the past is simply a part of its history, and your absence is its future. You have not erased yourself. You have simply moved to a different branch of reality, becoming a kind of time orphan, forever disconnected from your own origins. The popular film Back to the Future plays with a hybrid of these ideas. Marty McFly's meddling in his parents' past causes him to start fading from existence, a visual metaphor for the paradoxes of a single timeline model. But the eventual outcome, a new and improved present, suggests a kind of timeline editing that is more in line with a branching reality. Another proposed solution to the paradoxes is the Novikov self-consistency principle, which posits that the universe is fundamentally paradox-proof. Any action a time traveler takes in the past was always a part of that past's history. You cannot change the past because your actions were already factored into the timeline that led to your own existence. You are not an editor of history, but a character in a script that has already been written. The film 12 Monkeys is a brilliant and tragic exploration of this idea. The protagonist's journey into the past is not an attempt to change it, but a futile and predetermined loop, where his actions are the very cause of the events he is trying to prevent. He is a ghost in his own history, unable to alter the inevitable unfolding of a fixed, four-dimensional block universe. These different models of time travel, the branching multiverse, the self-consistent loop, are all attempts to grapple with the deep, logical puzzles of causality in a universe where the past might be accessible. But the introduction of higher dimensions adds another layer of complexity and possibility. If our four-dimensional space-time is just a brain floating in a higher dimensional bulk, as some theories suggest, then time travel might not involve moving backwards along our own timeline at all. It might involve taking a shortcut through the bulk, a wormhole that connects two distant points in our own space-time. This is the classic science fiction trope of a hyperspace jump, and it is an idea that has a tentative, if highly speculative, grounding in the mathematics of general relativity and string theory. But what about the 10th dimension, the conceptual point of origin that contains all possible realities, all possible timelines, all at once from this ultimate atemporal vantage point? The very concept of traveling through time loses its meaning. Past, present, and future are not a sequence to be traversed, but a single, unified, and timeless landscape. A time traveler, in this context, would not be a being moving from one moment to another, but a form of consciousness that could shift its point of awareness from one part of the block universe to another, experiencing different moments, different timelines, different realities, with the same ease that we shift our gaze from one object to another in a room. This is a level of reality that is far beyond our current comprehension, but it is a logical extension of the ideas we have been exploring. The binary viewpoint, with its cascade of yes/no decisions, provides a useful way to visualize this. Our experienced reality is one particular path through this infinite binary decision tree. A time traveler who changes the past is simply forcing a different branch to be taken at a particular node, creating a new, alternate history. But from the perspective of the entire tree, all branches coexist. Nothing is ever truly lost or changed. It is just a matter of which path is being followed, which story is being told. The paradoxes of time travel, then, are not necessarily logical contradictions that make it impossible. They are conceptual challenges that force us to expand our understanding of the nature of time, of reality, and of causality itself. They are a sign that our intuitive, linear, and single timeline view of the world is a profound oversimplification. The true nature of reality may be a far richer, more complex, and more wonderfully paradoxical tapestry of interwoven possibilities, a tapestry where every choice matters, and every path is, in some deep and mysterious sense, real. The quest to unify the fundamental forces of nature, to find a single, elegant theory that can describe all the phenomena of the cosmos, is the holy grail of modern physics, and the key to this quest may lie in the existence of unseen higher dimensions. The story begins in 1919 with a remarkable letter sent to Albert Einstein by a little-known German mathematician named Theodor Kaluza. Kaluza had made a startling and beautiful discovery. He had found that if he took Einstein's equations of general relativity, which described gravity as the curvature of a four-dimensional space-time, and reformulated them in 5 dimensions, something magical happened. The equations naturally split into 2 parts. One part was the original, four-dimensional theory of gravity. The other part was, to everyone's astonishment, Maxwell's equations of electromagnetism. It seemed that the electromagnetic force, the force responsible for light, for electricity, for chemistry, was nothing more than the curvature of a hidden 5th dimension. This was a breathtakingly elegant and powerful idea. It suggested that the two seemingly disparate forces of gravity and electromagnetism were just different aspects of a single, unified 5-dimensional geometry. Einstein was initially captivated by the idea, and he helped Kaluza to get his paper published, but the theory had a problem. Where is this 5th dimension? We do not perceive it in our everyday lives. In the 1920s, the Swedish physicist Oskar Klein proposed a solution. He suggested that the 5th dimension is compactified, curled up into a tiny, microscopic circle at every point in our space, a circle so small that it is completely invisible to us. This Kaluza-Klein theory was a beautiful and revolutionary idea, the first serious attempt at a unified field theory, but it ultimately failed to be a complete theory of nature. It could not account for the other 2 known forces, the strong and weak nuclear forces, and it made some incorrect predictions about the properties of particles like the electron. But the core idea, that the fundamental forces of nature could be a manifestation of the geometry of hidden, extra dimensions, was a powerful one that would lie dormant for decades, only to be resurrected in the 1980s with the rise of string theory. String theory, in its modern form, requires the existence of not just one, but 6 or 7 extra spatial dimensions to be mathematically consistent. And in this framework, the Kaluza-Klein idea is reborn in a much richer and more complex form. The different forces and particles we see in our universe are all determined by the intricate, multidimensional geometry of these curled-up Calabi-Yau spaces. This idea of a multidimensional reality is not just an elegant mathematical curiosity. It offers a potential, and deeply profound, explanation for some of the greatest mysteries of modern cosmology, the existence of dark matter and dark energy. Together, these two enigmatic entities make up 96% of the total energy density of our universe. The ordinary baryonic matter that makes up the stars, the planets, and ourselves is a mere 4%, a cosmic afterthought. We are living in a universe that is dominated by substances whose nature we do not understand. Dark matter is the invisible gravitational scaffolding of the cosmos. We see its effects in the rotation of galaxies and in the gravitational lensing of light, but we have never been able to detect the dark matter particle directly. Dark energy is the mysterious, repulsive force that is causing the expansion of the universe to accelerate. Its origin is a complete enigma. The idea of extra dimensions provides a new and tantalizing framework for thinking about these mysteries. In some brain world scenarios, the particles and forces of the standard model are confined to our three-dimensional brain, while gravity is free to propagate in the higher dimensional bulk. In this picture, dark matter might not be a new type of particle at all. It could be the gravitational influence of matter on a nearby parallel brain, a shadow universe separated from our own by a tiny distance in a fourth spatial dimension. We cannot see the matter on that other brain, but we can feel its gravity, leaking across the dimensions and creating the effects we attribute to dark matter. This is a speculative, but testable, idea. If dark matter is indeed a gravitational shadow from another dimension, it could lead to subtle, but detectable, deviations from standard general relativity on small scales, which could be searched for in high-precision laboratory experiments. Dark energy, too, could find a home in this multidimensional picture. It could be a manifestation of the energy of the bulk space itself, or a result of a force between our brain and other parallel brains. The accelerating expansion of our universe could be caused by the gravitational repulsion from a nearby massive brain in the extra dimensions. This would be a profound shift in our cosmological worldview. The destiny of our universe would not be determined by the matter and energy within it, but by its relationship with a larger, unseen, multidimensional reality. The concept of higher dimensions is one of the most exciting and mind-bending frontiers of modern physics. It is a frontier that is still largely theoretical, but it is one that holds the promise of a deeper, more unified, and more elegant understanding of the cosmos. It suggests that the reality we perceive is just a slice, a shadow, of a much richer and more complex multidimensional structure. And the great mysteries of dark matter and dark energy may not be mysteries about new substances in our universe, but clues that are pointing us towards the existence of new dimensions beyond our universe. The quest to find these hidden dimensions, whether through particle accelerators, gravitational wave detectors, or subtle cosmological observations, is one of the great adventures of 21st century science. An adventure that could one day reveal the true multidimensional glory of our cosmic home. The concept of control, The idea that we are the masters of our own destiny is one of the most cherished and perhaps most illusory of all human beliefs. We strive for it. We celebrate it. We build our societies and our psychologies around it. And yet, when we look closely at our own lives and at the world around us, we are constantly confronted with the limits of our own agency. The story of the person who, through sheer willpower, decides not to get sick, only to collapse with the flu the moment they take a vacation, is a familiar one. The anecdote of the cancer patient who visualizes their immune system attacking a tumor and experiences a miraculous remission is a powerful testament to the mind-body connection. But it is also a rare and exceptional event that is far from a controllable, reproducible technique. The 1993 Washington, D.C. meditation experiment, where a large group of meditators seemingly reduced the city's violent crime rate through focused, collective intention, is a fascinating and provocative data point. But it is also a study that has been heavily criticized for its statistical methodology and its lack of adequate controls. These examples hint at a reality where our consciousness can have a subtle but real influence on the physical world. But they also highlight the profound difficulty of isolating, understanding, and harnessing this influence in a predictable and controllable way. The universe, it seems, is not a simple, linear system that responds directly to our individual will. It is a vast, complex, and interconnected web of influences. A system where our own personal intentions are just one small thread in an immense and intricate tapestry. The framework of higher dimensions provides a powerful and beautiful way to visualize this complex interplay between individual agency and the larger collective reality. In the five-dimensional model of branching timelines, every choice we make, every action we take, creates a new path through the possibility space. Our free will is real, in that we are the ones who are choosing which path to follow. But we are not choosing in a vacuum. Our choices are constantly being influenced, constrained, and shaped by the choices of every other conscious and even non-conscious entity in the universe. We are part of a vast, consensual reality, a shared timeline that is the result of a constant, dynamic negotiation between trillions of different wills and intentions. Imagine your life as a single line, oscillating up and down on a graph. The horizontal axis is time, and the vertical axis is your state of being, your happiness, your health, your success. You may desire to keep your line consistently high, to live a life of constant triumph and joy. But your line is not an independent entity. It is entangled with the lines of everyone around you, your family, your friends, your community, your society. Their choices, their desires, their vibrations are constantly influencing your own. The physicist Christian Huygens in the 17th century discovered the phenomenon of entrainment, the tendency of coupled oscillators to synchronize their rhythms. He observed that two pendulum clocks mounted on the same wall would, over time, begin to swing in perfect synchrony. Our consciousness may behave in a similar way. We are constantly being entrained by the vibrational fields of the people and the culture around us. We are part of a collective, consensual dream. Psychoactive substances can create the temporary illusion of breaking free from this consensual reality, of charting a new, ecstatic path high above the baseline. But this is often a false freedom. The crash that follows can leave us even more deeply enmeshed in the negative, downward pull of our own and the collective shadow. True freedom is not about escaping the system, but about becoming a more conscious and intentional participant within it. It is about learning to navigate the complex currents of the collective field with wisdom, with compassion, and with a clear sense of our own unique purpose. It is about understanding that while we cannot control the entire ocean, we can learn to become skillful sailors of our own small vessel. This brings us to the deep and often difficult question of personal accountability. In a universe of such vast complexity and interconnectedness, it can be easy to feel like a victim of external forces, to blame our circumstances on bad luck, on an unjust society, or on the ill intentions of others. And there is no doubt that these external factors are real and powerful. But the dimensional viewpoint also reminds us that at every moment, we are making choices, we are collapsing possibilities, we are co-creating our own reality. To take responsibility for our lives is not to deny the existence of external constraints, but to focus on our own unique sphere of influence, to become more conscious of the choices we are making, the stories we are telling ourselves, and the vibrational energy we are putting out into the world. It is to recognize that even a single, small, and conscious choice can send ripples of change throughout the entire interconnected system. But even as we embrace our own creative power, we must also embrace our limitations. Our human consciousness, as extraordinary as it is still just one finite perspective within an infinite, multidimensional reality. The higher dimensions of existence, the realms of other universes, of other physical laws, of realities that are beyond our current capacity to even imagine, these will likely always remain beyond our direct control or even our comprehension. We are both powerful creators and humble participants, masters of our own small corner of the cosmos, and children in a much grander and ultimately mysterious universal home. The illusion of control, then, is a double-edged sword. To believe that we have no control is to succumb to a state of helpless victimhood. To believe that we have total control is to fall into the trap of arrogant delusion. The path of wisdom lies in the middle, in the graceful dance between agency and surrender, between shaping our reality and being shaped by it. It is the recognition that we are both the artists and the clay, the dreamers and the dream, the individual notes and the grand cosmic symphony. And it is in the holding of this beautiful, paradoxical, and life-giving tension that we can find our true power, our true freedom, and our true place in the vast, interconnected, and endlessly creative unfolding of the cosmos. The 10th dimension. In the conceptual hierarchy we have been exploring, represents the ultimate, all-encompassing reality, the point of origin and the final container for all of existence. It is a concept that is so vast, so total, that it pushes our language and our imagination to their absolute limits. It is the realm where all possibilities, all timelines, all universes, all physical laws are not just potential, but are, in some deep and mysterious sense, actual. To visualize this, let us return to our analogy of the dimensional camera. A first-dimensional camera would just capture a single point. A second-dimensional camera could capture a line. A third-dimensional camera, like our own, captures a flat, two-dimensional image of a three-dimensional world. A fourth-dimensional camera would capture an entire world line, the complete history of an object from its birth to its death, all at once. A fifth-dimensional camera would capture the entire branching tree of all possible histories for a particular object. A sixth-dimensional camera could capture the entire phase space of all possible histories of our entire universe, given its specific initial conditions and physical laws. A seventh, eighth, and ninth-dimensional camera would capture the vast cosmic library of all possible universes, with all their different laws and initial conditions. The 10th-dimensional camera, then, would be the ultimate, final snapshot. It would be a single, dimensionless point that contains, within it, all of these other dimensions, all of these other possibilities, all at once. It is the point of infinite density, not of matter, but of information. It is the everythingness from which the somethingness of our experienced reality emerges. This is a concept that has deep resonances with the ideas of many of the world's mystical and philosophical traditions. The Brahman of the Vedanta, the Ein Sof of the Kabbalah, the Tao of Taoism, these are all attempts to name the unnameable, to describe the ultimate, undifferentiated, and all-encompassing ground of being from which all manifest reality arises. The 10th dimension, in this conceptual sense, is not a place we can travel to. It is the source we have come from. And it is a source that is, in principle, beyond our ability to fully comprehend. The Austrian logician Kurt Gödel, in his famous incompleteness theorems, showed that any formal mathematical system that is complex enough to contain basic arithmetic will always contain true statements that cannot be proven. Within that system, to prove them, you need to step outside the system and use a larger, more comprehensive set of axioms. But this new, larger system will have its own new set of unprovable truths, and so on. In an infinite regress, Gödel's theorems are a profound statement about the inherent limitations of formal systems. And if our universe is, as some have suggested, a mathematical structure, then Gödel's theorems imply that it can never contain a complete and consistent description of itself. There will always be aspects of reality that are true but are unprovable from within the system. The 10th dimension, in this light, can be seen as the ultimate meta-system, the all-encompassing reality that contains all the other limited systems, but which cannot itself be fully described or understood from within any of them. It is the ultimate context, the final undrawable frame of the cosmic picture. The theory of superstrings provides a more physical, if no less abstract, picture of this ultimate reality. In this theory, all the particles and forces of our universe are the result of the different vibrational modes of tiny, one-dimensional strings. And these strings are thought to be vibrating in a 10-dimensional space-time. The specific way in which the extra 6 dimensions are curled up, the geometry of the Calabi-Yau manifold, is what determines the specific spectrum of vibrations, and therefore, the specific set of physical laws and particles of our particular universe. The 10th dimension, in this picture, is the fundamental, underlying reality in which the cosmic symphony of the strings is played. The different universes of the multiverse correspond to different possible geometries, different possible symphonies. Our universe is just one particular piece of music, one particular solution to the fundamental equations of string theory. The concept of the 10th dimension also sheds a new light on the seemingly intractable paradoxes of our own experience, like the paradox of Zeno, which argues that motion is impossible because to get from point A to point B, you must first cross half the distance, and then half of the remaining distance, and so on, in an infinite series of steps, in a classical, continuous space-time. This is a real logical puzzle, but in a universe where space and time may be quantized at the Planck scale, where there is a smallest possible unit of distance and a smallest possible unit of time, the paradox dissolves. The infinite regress is halted by the fundamental, discrete nature of reality itself. In a similar way, the 10th dimension, as the ultimate foundational reality, can be seen as the ultimate quantifier, the point that halts the infinite regress of why questions. Why are the laws of physics the way they are? Because they are the result of the specific geometry of the extra dimensions. Why this geometry? Because it is one of the many possible solutions to the equations of string theory. Why string theory? Why 10 dimensions? At some point, the chain of explanation must end, not in an arbitrary fact, but in a final, all-encompassing, and self-consistent structure. The 10th dimension, In this conceptual framework is that final structure. It is the ultimate, it is what it is. This is not a dismissal of the question, but a recognition of the limits of explanation. It is an invitation to a state of profound intellectual and spiritual awe, a state of learned ignorance in the face of a reality whose ultimate nature is so vast, so complete, and so all-encompassing that it can only be pointed to, hinted at, and wondered about. It is the silent, dimensionless, and infinitely pregnant point from which all the beauty, all the complexity, and all the wonder of our multi-dimensional cosmos is born. The intricate tapestry of reality, as woven by the threads of quantum mechanics and higher dimensions, is a reality of profound interconnectedness. The different dimensions are not separate, isolated realms. They are layers of a single, unified structure, constantly interacting and influencing each other. And our own experience, our own consciousness, is not a separate, detached entity. It is a point of intersection, a place where these different layers of reality meet, overlap, and create the rich, multifaceted world we inhabit. To understand this, let us consider the interplay between what we can call physical systems and mimic systems. A physical system is the world of our three-dimensional bodies, of matter and energy, of the deterministic cause and effect laws of classical physics. A mimic system, a term coined by the biologist Richard Dawkins, is the world of ideas, of beliefs, of cultures, of stories. It is the abstract, informational realm of the mind. These two systems are not separate. They are in a constant dynamic feedback loop. Our physical reality shapes our thoughts and beliefs, and our thoughts and beliefs, in turn, shape our physical reality. A new scientific theory, a meme, can lead to the development of a new technology that fundamentally alters our physical world. A powerful religious or political ideology can shape the course of history, leading to the rise and fall of empires. This interplay between the physical and the mimic can be visualized in our dimensional framework. Our physical lives unfold along a specific four-dimensional timeline, a particular path through the fifth-dimensional possibility space. But our mimic lives, the lives of our ideas and beliefs, are not so constrained. An idea can travel across time and space. It can connect different cultures. It can influence the choices that lead to the branching of different timelines. The mimic system exists, in a sense, at a higher dimensional level, a level that can create interference patterns between the different potential realities of the physical world. A powerful shared belief, a dominant meme, can act as a kind of observer, collapsing the wave function of a collective reality, steering the course of a society or a civilization along a particular path. A cultural revolution, a scientific paradigm shift, a spiritual awakening. These are all moments where a new mimic pattern creates a powerful interference effect, fundamentally altering the shape of our shared physical timeline. This concept of interference and overlap is not just a metaphor. It is a deep feature of the quantum world. The interference pattern in the double-slit experiment is a direct result of the overlap of the two possible paths of the electron's wave function. And in the higher dimensional reality of string theory, the properties of our universe are determined by the complex interference patterns of the vibrating strings as they move through the multidimensional Calabi-Yau space. Our experienced reality is an interference pattern, a product of the overlap and interaction of a vast number of underlying potential realities. We, as conscious beings, are the points at which this interference becomes manifest. We are both the product of our physical, four-dimensional reality, and the conduits for the higher dimensional, mimic systems that flow through us. We are living at the intersection of worlds. This perspective gives us a new and powerful way to understand the tension between determinism and free will. Our physical bodies are subject to the deterministic laws of physics. Our lives are constrained by the circumstances of our birth, by the society we live in, by the history that has preceded us. This is the particle aspect of our being, but our minds, our consciousness, have access to the wave aspect, to the higher dimensional realm of possibility, of imagination, of choice. We have the freedom to introduce new ideas, new memes, into the system, to create new interference patterns, to choose which possibilities to collapse into our shared reality. Our free will is not the freedom to violate the laws of physics, but the freedom to navigate the possibility space that those laws allow. It is the freedom to choose which story to tell, which dream to follow, which future to create. The universe, in this view, is a vast information processing system, a cosmic computer that is constantly exploring its own infinite computational potential. And we, as conscious mimic beings, are the universe's own agents of exploration, its own way of introducing novelty, of creating new patterns, of pushing the boundaries of what is possible. This brings us to a final, profound, and deeply humbling realization: the journey to understand the universe, from the smallest quantum flicker to the vastest cosmological structures, is not just a journey out there. It is also a journey in here. The same principles of superposition, of uncertainty, of entanglement, of dimensional overlap that govern the cosmos are also at play in the deep, mysterious, and endlessly creative landscape of our own consciousness. The structure of the universe and the structure of the mind are not two separate things. They are reflections of each other, two different expressions of the same, underlying, informational reality. The cosmic web of galaxies and filaments is mirrored in the neural web of our own brains. The branching timelines of the multiverse are mirrored in the branching possibilities of our own choices. The creative power of the quantum vacuum is mirrored in the generative silence of our own deep, contemplative states. To study the universe is to study ourselves, and to study ourselves is to study the universe. We are not just in the cosmos is in us. This is the ultimate, non-dual truth that lies at the heart of both the most ancient spiritual wisdom and the most advanced modern science. It is a truth that can be intellectually understood, but can only be truly known through direct, subjective experience. And the most universal and accessible portal to this experience is the nightly, sacred, and deeply mysterious journey of sleep. In sleep, we let go of our attachment to the collapsed, classical world of our waking identity, and we dissolve back into the quantum, superpositional, and multidimensional sea of pure potential. We become the universe, dreaming itself. We are the interference pattern between the seen and the unseen, the known and the unknown, the finite and the infinite. And in this beautiful, paradoxical, and life-giving dance, we find our true home, our true nature, and our true place in the grand, magnificent, and endlessly unfolding story of the cosmos. The concept of a 10-dimensional reality, while a cornerstone of advanced theoretical physics like string theory, remains one of the most challenging ideas for the human mind to grasp. Our entire evolutionary history has conditioned us to perceive and navigate a world of 3 spatial dimensions and 1 of linear time. To venture beyond this familiar framework requires a leap of imagination, a willingness to embrace abstraction, and a deep appreciation for the power of mathematics to describe realities that lie beyond the reach of our senses. The journey to the 10th dimension is a journey of conceptual scaffolding, building layer by layer, from the simple and intuitive to the complex and counterintuitive. We begin with the 0th dimension, a single, dimensionless point. It has no size, no extension, it is pure location. This is the ultimate abstraction, the conceptual seed from which all of geometry grows. From this point, we can extrude a line, creating the first dimension, the world of pure length. A being in this one-dimensional world could only move forward or backward along this line. The second dimension is created by adding a new direction, perpendicular to the first, creating a plane, a world of length and width. This is the world of flatland. The famous thought experiment proposed by the 19th century schoolmaster Edwin Abbott, the inhabitants of flatland. Two-dimensional shapes like squares and triangles can move left and right, forward and backward, but they have no concept of up or down. A three-dimensional object, like a sphere, passing through their two-dimensional world would appear as a mysterious and magical event, a point that grows into a circle, and then shrinks back to a point before disappearing completely. For the Flatlanders, the third dimension is a realm of incomprehensible, godlike power. And this is a powerful analogy for our own relationship with the higher dimensions. We are the inhabitants of a three-dimensional space-land. By adding a third direction, depth, we gain the world of solid objects, of volume, of the rich, physical reality we experience every day. But what if our three-dimensional world is just a slice, a cross-section, of a higher dimensional reality? The fourth dimension, in the most common physical interpretation, is time. But it is not the flowing, transient time of our subjective experience. It is a spatialized time, a dimension along which the entire history of the three-dimensional universe is laid out. A four-dimensional being could perceive our entire lifespan, from birth to death, as a single, static, four-dimensional object, a space-time worm. They could see all the moments of our lives at once, just as we can see all the points on a line at once. This block universe view is a direct consequence of Einstein's theory of relativity, and it is a profoundly deterministic picture of reality. But the story does not end there. The fifth dimension, in the conceptual framework we are building, introduces the idea of possibility, of alternate realities. If every quantum event, every choice, causes the universe to split, then the fifth dimension is the space that contains all these branching, parallel timelines. A fifth-dimensional being could not only see our entire history, but could also see all the other possible histories that could have unfolded from the same starting point. They could see the you who took the other job, who married the other person, who made the other choice. The fifth dimension is the landscape of the might-have-beens. The sixth dimension takes this a step further. It is the plane that contains all of these possible histories, all of these branching timelines that arose from the specific initial conditions of our Big Bang. And it allows for a folding of this possibility space, a shortcut between different, seemingly distant branches. It is the complete phase space of our particular kind of universe. The seventh dimension marks a profound leap into an even greater level of abstraction. It is the dimension that contains the set of all possible universes that could have started with different initial conditions and different physical laws. This is the realm of the Level 2 multiverse of eternal inflation, a library of all possible cosmic beginnings. In one universe, gravity might be a repulsive force. In another, there might be 4 spatial dimensions. In a third, the speed of light might be different. The seventh dimension is the space that contains all these different and mutually inaccessible cosmic rulebooks. The eighth dimension is the plane that contains all of these different seventh-dimensional libraries, allowing for a branching, a comparison between these fundamentally different kinds of realities. The ninth dimension is the ultimate ensemble, the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the set of all possible universes, the complete catalog of all that is physically possible. And this brings us, finally, to the 10th dimension. In this hierarchical, conceptual model, the 10th dimension is the ultimate point of origin, the dimensionless, abstract point that contains, within it, all of the other, lower dimensions, and all of the infinite possibilities they represent. It is the point of everythingness, the ultimate ground of being from which all manifest reality, in all its infinite variety, unfolds. It is a concept that is almost pure metaphysics, a point where the language of physics and mathematics touches the language of mysticism and philosophy. But it is a concept that has a more concrete, if no less abstract, home in the framework of superstring theory. The mathematical consistency of superstring theory, the leading candidate for a theory of everything, requires a 10-dimensional space-time. In this theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the different ways these strings can vibrate, the different notes they can play, are what give rise to the different particles and forces we see in our universe. The properties of these vibrations are determined by the geometry of the 6 extra compactified dimensions. So, the 10th dimension, in this more physical picture, is the fundamental, underlying arena in which the cosmic symphony of the strings is played. The landscape of the 10 to the power of 500 possible vacuum states of string theory corresponds to the vast multidimensional possibility space we have been exploring. Each possible way of curling up the extra dimensions corresponds to a different possible universe, a different set of physical laws, a different symphony. Our universe is just one particular, beautiful, and life-bearing piece of music, played on the 10-dimensional instrument of the cosmos. This journey through the dimensions is a powerful exercise in expanding our own conceptual horizons. It is a journey that takes us from the familiar and the concrete to the abstract and the unimaginable. It is a journey that should instill in us a profound sense of humility, a recognition of the severe limitations of our own three-dimensional perception. And it is a journey that should also fill us with a sense of wonder, a wonder at the possibility that the reality we experience is just a thin, fragile, and beautiful membrane, a single slice of a much grander, much richer, and much more mysterious, multi-dimensional cosmos. The 10th dimension, whether as a conceptual endpoint or a physical reality, is a powerful symbol of the infinite, creative potential that lies at the heart of existence, a potential that is both the source of our universe and the source of our own. Endless capacity to imagine, to question, and to explore. The participatory nature of reality, as suggested by the strange and beautiful world of quantum mechanics, is one of the most profound and revolutionary ideas in the history of human thought. It is an idea that challenges our most basic common sense assumptions about the world. And it is an idea that is still, a century after its birth, the subject of intense debate and a source of deep philosophical unease for many. The classical, Newtonian worldview, which has shaped our thinking for 300 years, is a worldview of a clockwork universe, a universe of solid, definite objects moving in a fixed, absolute space and time, governed by deterministic laws. It is a universe that exists out there, independent of our own minds, a universe that we can, in principle, observe and understand without affecting it. Quantum mechanics shatters this picture. It tells us that at the fundamental level, reality is not a collection of definite things, but a web of interconnected probabilities. A particle does not have a definite position or a definite momentum until it is measured. It exists in a superposition of all possible states, a wave function that describes the probability of finding it here or there or with this momentum or that one. And it is the very act of measurement, of observation, that seems to be the mysterious ingredient that collapses this wave of probability into a single, definite reality. This is the observer effect, the strange and unsettling fact that the world we see seems to be, in some deep and fundamental way, shaped by the very act of our seeing it. This has led to a host of perplexing questions and a zoo of different interpretations. Does this mean that we are literally creating reality with our minds? The answer for most physicists is a qualified no. The observer effect is not about a mystical power of consciousness to will things into being. It is a consequence of the fact that any act of measurement, any interaction with a quantum system, is a physical process that necessarily disturbs that system. To measure an electron, you have to bounce a photon off of it, and this interaction inevitably changes its state. In this view, the observer does not need to be a conscious being. A simple, inanimate particle detector is enough to cause the wave function to collapse, but this just pushes the mystery back a step. What is it about the interaction with a macroscopic, classical measuring device that is so special? Why does it have the power to collapse the quantum superposition? This is the heart of the measurement problem, and it is a problem that has not been definitively solved. The decoherence program has provided a partial answer, showing how a quantum system rapidly loses its superpositional nature as it becomes entangled with the vast number of degrees of freedom in its environment. But decoherence does not explain which specific outcome is chosen from the initial superposition. It just explains why we do not see macroscopic superpositions. The many worlds interpretation offers a radical and elegant way out of this puzzle. It simply denies that the collapse ever happens. The wave function is the complete and total description of reality, and it always evolves in a smooth, deterministic way according to the Schrödinger equation. When a measurement is made, the universe does not collapse into a single state. It branches. The observer becomes entangled with the system, and the entire world splits into multiple parallel realities, one for each possible outcome. In one branch, the electron is found at position A. In another, it is found at position B. There is a version of you that experiences each outcome. In this view, we are not collapsing reality. We are simply experiencing one particular branch of a vast and constantly splitting quantum multiverse. This is a breathtakingly grand and logically consistent picture, but it comes at the price of accepting an almost unimaginable ontological extravagance and infinite number of parallel, unobservable worlds. But regardless of which interpretation one prefers, the central, participatory nature of the quantum world remains. We are not detached spectators of a pre-existing reality. We are entangled participants in a cosmic drama, a drama where the questions we ask, the measurements we make, the choices we take, all play a crucial role in shaping the reality that unfolds. This has a powerful and direct parallel in our own subjective lives. The reality we experience is not a passive reception of external data. It is an active, co-creative process. Our beliefs, our expectations, our attention, all act as a kind of filter, collapsing the infinite, superpositional potential of the world into a single, experienced reality. If we believe the world is a hostile and dangerous place, we will tend to notice and amplify the evidence that confirms this belief. If we believe the world is a place of beauty and opportunity, we will tend to experience a reality that reflects this. Our consciousness is not just a mirror reflecting the world. It is also a lamp that illuminates it, and in illuminating it helps to bring it into being. This does not mean that we have absolute, solipsistic control over reality. We are still bound by the underlying probabilistic laws of the wave function, both in the physical world and in our own psyches. But we do have a choice. We have the choice of where to direct our attention, which questions to ask, which possibilities to engage with. And this choice is a creative, world-shaping act. This is the deep and beautiful truth that the participatory universe reveals to us. It is a truth that calls us to a new level of responsibility, a new level of conscious participation in the ongoing creation of our own lives and of our shared world. And it is a truth that can be most profoundly felt in the quiet, creative, and dreamlike spaces of our own inner world, a world where we are, at every moment, both the artist and the canvas, the observer and the observed, in the grand, magnificent, and endlessly unfolding masterpiece of reality.